Important. Okay, friends. So we're talking about big O notation. Big O notation is a mysterious sort of idea. Really, especially when you're first learning how to code, it's like, I don't understand what that means, but it's a way that we can understand the behaviors of our functions or our computer or our processes that we're creating. Let's think about it this way. Let's say that I had a function, right? And I need to know, well, what's the most optimal way to do something? What you'll find is usually the process of creating a product is first off, you get it to work, right? So the first and foremost thing is get it to work. And I will always tell you this, especially when you get to algorithms, brute force it at the beginning. Brute force just means even if you know that it's not a great, not great code, but it's going to work, like you can get it to work. That is the first and foremost, most important thing. And even in a job interview, again, brute forcing and just trying to, and getting it to work is a really important thing. The next step after getting it to work is then going and refactoring that. Okay, now how do I improve this? How do I make it better? What can I do to make this better, more efficient, more optimal, depending on your use case? And it's just iterations of that, of making it better, making it faster. That's really all software is. It works, and then we say, how do we make it faster? How do we make it better? And then we just keep iterating onto that. Now, there's not necessarily a way for us to, or sorry, let me backtrack. When I say make it faster, make it better, unfortunately, there's not a baseline. What do I mean by that? Well, here, one idea you might think, or let me ask you this, when I say make something faster, what do you guys initially think of? When I'm saying that, how would you gauge if something's faster than something else?
Processing speed.
Processing fee, is that what you said?
Processing speed.
Oh, processing speed. Yeah, how fast it is, right? So you're going to compare the two speeds. That's a great idea. What else? How else could we determine if one's faster than another? Like very rudimentally. Think about two people. How do we tell if two people are faster than one another?
Whoever finishes first or gets it first, whichever
Yeah.
loads first.
Yeah, like think about we just had the Olympics. We have two runners that are running the 100-meter dash, and they both say that they're the fastest, right? Or the best. Or maybe they don't say that, and we just want to say, well, who is the fastest? Now, we don't have a way necessarily to put two algorithms and run the same race, but one thing we could do is say, okay, you run over here and you run over here, and you guys run the same distance, do the same algorithm, and whoever's the fastest is, we know who's faster, right? So Usain Bolt versus, whoever, we can tell by the time, right? We use a time speed, it's 9 seconds, it's whatever. Well, that might be a good idea for thinking about it, right? Of how do we tell if an algorithm is faster? So you might initially think, well, that sounds like a good idea. So here I've got this array that just has 5 values in it, and I've got a function called print array. And all it does is it takes in an array. We use a for loop, and then it console logs that array there, or console logs the value. So it's just all this function does, iterates through my for loop and prints each value. Now there's this thing in JavaScript that's built in, so similar to console log. This one's called console.time. And what you do is you pass in the function you want to time, you run the function, and then you pass in the end of that function run. So this is a way that we can actually do a speed test to see how fast my algorithm is. So you might think, okay, great, that's the easiest way to do it. But we run into a problem when we deal with this. If I were to run this, we get, okay, here's my for loop. It's done running. It did everything I wanted it to do. It console logged. Here's my function. That's just part of the console log.time print array. And it is my time in. This took 1.794 milliseconds to run. Great. And so you might say, okay, awesome. This takes 1.794. This is my baseline. But look what happens whenever we write it again. Or we run it again, sorry. Now it's 1.696 milliseconds. I run it again. 645, run it again, 8.97 milliseconds, or 1.897. And so you see that actually timing out the algorithm doesn't really make sense. And it doesn't work because there's so many factors around how this algorithm's running, right? What computer I'm currently using, the inner workings of that, the chip, all the processing power, how many apps I currently have open, so that way how much memory I can have dedicated to this. There's too many outside things that are happening for us to actually take a time and do a comparison. So something that we do is we sort of create a baseline called Big O notation, or time and space complexity. Time and space complexity obviously deals with the time or the space of a function and how long or how it's affected as n increases. We're going to talk about that in a second. And it's just a tool that we use to measure the efficiency of an algorithm. Again, we can't just do an actual timing piece to say, okay, this is faster, because there's so many factors going in. What we can use is some math to understand and say, okay, what is the speed, or how can we assume this function is going to run? Now, one thing to note is usually 99% of the time when we're talking about Big O notation, we're talking about worst case scenario. We're going to talk about that in a second, but we're talking about worst case scenario situation. Now, time complexity is the measure that we use for how fast an algorithm runs. Space complexity is a measure of how much memory that algorithm uses. Cool. So time complexity, Big O of time is might be how you hear it. Big O of time is how fast an algorithm runs, and Big O of space is how much memory that algorithm uses. Memory being like if we're creating new things, copying arrays, stuff like that. So how does this look? What does this look like? This is going to get a little mathy, but just stay with me. There's really three that I want to talk about right now, and I think just kind of keep it base. And we can visualize these by making a graph. Now remember, this is all dependent on when n changes size, right? As n increases, here's what happens to our algorithm. Does anybody know what n represents when we're dealing with like code or algorithms? What does n represent?
Just the number?
Is that
Yeah,
log?
right. If I just say an array with n values, so this is something common you'll hear, like an array with n values. N just represents and says it can be any number, right? So as n increases, so as the amount of values in my array increases, what is happening to the time it takes my algorithm to run, right? And so let's say that I've got this algorithm. It's starting at 0, right? And as it increases to 5, or as it has 5, it increases. And especially because I'm doing a for loop here, what's happening? What is this for loop doing?
You're running.
It's running, but what is it doing? Thinking about the computer, it's happening mega fast, but it's going through each value, right, of my array. It's going to go here, and it's going to go here, then here, then here, then here, right? And so you can think about it. This is probably pretty quick, right? And it is pretty quick. We just saw that whenever we timed it. This is pretty quick. But let's say that instead of 5, I had 100 or 1,000 or 1,000,000 values. What's going to happen to my algorithm? Is it going to go at the same speed as it did with 5, or is it going to increase or decrease, or what do you guys think?
It'll slow down.
It'll slow down, right? It'll take longer. And so with that, we could assume and say, hey, as we get more values, as my array increases, the amount of time it's going to take to run specifically this algorithm is going to increase, right? If I've got to count 5 things, that's pretty quick. If I have to count 500 things, that takes a little bit longer. And if I count 5,000 things, that takes even longer, right? Does that make sense? And so that is what we call O of n, or it's a linear time and space complexity. What that means is we look at our algorithm and we understand what it's doing. We know this is going to go through every value in my array. And so we say, well, as my array gets bigger, the amount of time it's going to take also gets bigger, right? There's a correlation. So as n increases, as the amount of values in my array increases, the time increases. This is what we call O of n. O just represents big O notation, and then n represents the time it's going to take, right? Does that make sense? Any questions on that? I just want to pause there. Cool, Taryn's getting it. Shane, cool. Now, let's think about this. What if I said what if my function, let's rewrite this a little bit. And I wanted to console log array of 1. What happens if my array increases to 1,000,000? Am I doing any extra steps? Am I going to have to, is it going to be more of a challenge? Like, is it going to take longer to do this? If I've got 1,000?
For the input or the output?
Let's say that I've got this array right here of 5, and all this function, remember, all we're caring about is time and space complexity of this print array function. And let's pretend all my function's doing is it's going and it's printing out the second value in my array. No matter what, right? So here, if it's 5 or there's 5 values in there, it prints out the second value. Let's say that there's 5 million values in here. Is anything changing on our operations?
It shouldn't.
It shouldn't, right?
No. Yeah.
And so it's easy to say, or it's feasible to say that it doesn't really matter the size of my array. It could be 5 trillion values. All I'm doing is getting this second value. Doesn't change whether my array is only 5 values or 5 million values. The actual process is not changing. Here, whenever we had our for loop, it changes, right? Because now I have more values I have to go through. I have to go through the entire array. When I'm just grabbing this value at this second position, it doesn't matter, right? It doesn't matter how large my array, as long as there's 2, right? That's the assumption. But as long as it's really, there's 2 or more values, it doesn't matter. Is that so? Would you guys just agree with that statement?
Yes.
Yeah. So with that, when we have something like that, right? That's what we call O of 1, or our constant time. O of 1. Again, this is just a very beginner's course. We're going to go into more stuff with this as we go because it can get a little bit nuancey, but I'm going to show you like the 3 big ones, or 3 of the big ones. And then we can sort of, go from there. O of 1 represents constant time. Constant time, right? Meaning that it doesn't matter the size of my array. It's going to take the same amount of time no matter what. When we're looking at just grabbing a value or reading at a specific memory location, it is always going to be constant time. Because we just saw that, right? It doesn't, and we sort of thought through that. It doesn't matter if I have 5 million or I have 5 values. I'm still just grabbing the second value of the 5 million, or I'm grabbing the second value of the 5. It's the same thing. So that's what we call O of constant time. When we are dealing with algorithms, the least amount of time it takes, the most optimal. So O of 1 is the most optimal you can get. That's not always achievable. So sometimes in an algorithm, you can't achieve O of 1 constant time because you have to do some sort of manipulations. But when you're looking at certain things, or you're trying to decide certain things, O of 1 is the most optimal you can get. You can't get any better of an algorithm. You can't get more efficient than O of 1 time. Does that make sense? Now, on the inverse, maybe not inverse, when we're talking about space, it's the same exact thing. Time and space complexity still use O of n, O of 1. They're doing the same thing. One's just talking about how much time an algorithm takes to run. And the other talks about how much memory an algorithm uses. Now, let's say that for each of these, if I had a for loop, let me delete some of this stuff. I still want to keep that. If I had a for loop and I was also creating a new array or doing something, right? And I was creating a new variable and saving it, or I was, doing something, pushing each value to a new array. Well, now as n increases, my space I need in memory also increases, right? Because if this is 5 million values and I'm creating 5 million new arrays or new variables, well, then all of a sudden my space is linear to how many values n gives me. And so just wanted to point out that they are like interchangeable in the sense of just thinking about one is how fast it is, the other is how much memory it takes up. But based off of that, we can understand time and space complexity. Now, the last one I want to talk about is what if I got something like this? If I've got something like this, what's happening here? Here I've got my for loop, right? And with each iteration, I am starting J at, we'll start J at, we'll start J at 0. But when we're thinking about our code, what's happening here? We don't actually have to code it out, but what's happening here? Let's kind of step through it as we go, right? I've got this for loop. So my I is 0. And I'm going to go through my array length, which is good. So it enters in. Then I create another variable, J, that's equal to 0. And then I go through this entire array in console log I, which is going to be 0. And I console log J, which is 0, right? Well, I don't automatically go up to I and then say now I is 1, right? Because with a for loop, I have to finish my for loop. I have to wait until this condition is no longer true. So now J becomes 1. And then I console log 0, 1. Because I is still 0. J becomes 2. I go, 0, 2. And I keep doing that over and over and over again. Right? This is what we call, does anybody know what this is called?
Nested for loops.
Yeah, exactly. This is what we call a nested for loop. But if we're thinking about what it's doing, it's going through each array, or it's going through the array how many times?
25.
Yeah, it's going through a lot. Yeah, exactly. 25. Because it's going to go through all of J, and then I becomes 1. And then what happens? J equals 0. And then we go through and keep going, right? And then 0, 1, 2, 3, 4, 5, I becomes 2. J is established as 0 all the way through 5. And it keeps doing that. Because there's 5 values. And just like Eric said, 25. Anybody, 5 times 5 is 25, right? So if n, in this case, n is 5, because there's 5 values in my array, what is this equal to? Think about this right here, right? What is another way to write this?
5 squared?
Yeah, 5 squared, right? Or what is representing 5 is n.
And
Yeah, so then we have n squared. This is the most math we're gonna have to do today. So if you're like, what's going on? What's happening? But remember, n represents the 5 of the value. So 25 is the same way as saying n times n. And n times n we know is n squared. So there is, because we have to iterate through double loops, just like this, there is a time and space complexity called O of, as you guessed it, n squared. And as you could tell, because I am iterating through this loop, not just one time, but at least 2 times, it's going to be a lot slower than O of n. It's going to be a lot slower than O of n. And so these are the big 3 that I kind of wanted to talk about today. And just to get you guys to start understanding why we use time and space complexity, and then looking at this and saying, okay, great. I see that this is double for loops and I'm iterating through multiple times. At the worst case, this is O of n squared. Does that make sense? Those 3 sort of examples, do those make sense? Oop. Now, why do I say worst case? And does anybody know maybe why we use worst case? Why wouldn't we use best case? Don't we always want to do, what's the most optimal?
It's a barometer. You know, you could deal with worst case and make a decision worse than.
Yeah, exactly, right? The other thing, and the reason we do it is exactly, I mean, first on Trail, exactly, right? Like, don't tell me what the best case is, and then, the worst case happens and it's way worse than I thought. Like, just let me do that and I can adjust accordingly. But let's think about this. Let's say my function, cool, print array does that. That's great. Now let's hypothetically say that I've got this array and I've got a function called find value. And what it does is it goes through and checks each value to say, is that there or not? So maybe I want to, we don't need a console log time, but maybe I want to console log find value array, and I want to find the number 5. Maybe I just want to return found it. And then, yeah, -1, and it's fine. If I didn't see it, if I don't see it. Now this function, at the best case scenario, this is what happens, right? The fastest, most optimal situation would be that, hey, we're going to iterate through this. We're doing a for loop. We're going to check the first value, the position 0. And it's going to say, is this the value that we passed through, which is 5? And the best situation is that that number is right here, right? Cool, it's the first one. We found it, easy peasy. We're done, right? It's super duper fast. Now, that doesn't explain what is always going to happen in the real world, or that's not saying that it is that fast, typically. Because what if it was something like this? It would have to go through the entire array, and then the last value was 5. Or let's say it doesn't even exist. And it has to go through the entire array just to find that it doesn't exist. So that's why we would do worst case scenario, because it's not always the most optimal, right? The most optimal would be that it's, the first value and it's good, but not everything's sorted. Data is not always that great. So we look and say, okay, the worst possibility it could be is it's the last value I look, and or it's not even in there. And so I have to go through the entire array. Therefore, it's, this is the time and space complexity. Can anybody tell me what would the time and space complexity be of this function? You don't even have to do space. Well, yeah, you could do space if you really wanted to, but what is the time and space complexity of this?
How fast it runs?
Well, yeah, how fast it runs, but can you tell me, right? We just talked about 3 different options of what it is, of what it could be. What is it?
O in a 5.
Oh, in a 5?
My hypothesis.
Is
Oh,
it?
okay.
Okay.
Yeah, Jennifer, it is. It's O of n, right? Because worst for time complexity, it's O of n. Because worst case scenario, we have to go through the entire array full of n values. We don't know how big the array is. So we're just saying, hey, however large the array is, that's how long it's going to take, right? If it's shorter, then okay, it might be quicker than if it's 1,000,000 values here. But because there is a possibility that 5 is either at the end and or does not exist, we have to go through the entire array to assure. At the worst case scenario, we have to go through the entire array to find out that either it's the last value or it doesn't exist. And because of that, the time it's going to take to run this in a worst case scenario situation is however long the array is, or however many n values there is, or yeah, however many values there are in the array. Does that make sense?
Well, but to be clear, to be O of n, you just go through the array one time. As
Yes.
opposed to O of n squared, which is you go through it, you go through each one the length of the array. So O of n is just you go through the array once.
Yeah, like
Okay.
if we were this right here, we're looking and trying to find the value, and if it's not there, then we're returning a -1, right? So we only need to go through one time to find that value. If we go through the entire thing and it's not there, we return -1, or not there. And if we do find it, we say yes. But because we have to go through the entire array just one time, that's O of n, because however big the array is, that's how long it's going to take, right? Or a better way to say it is the time it's going to take to run is affected by however long or however big the array itself is. So it's super contingent on the size of the array. Think about the graph. As increases, as more values are there, it's going to take a little bit longer. And a little bit longer and a little bit longer as it keeps going. Anybody want to give their guess on space complexity? Anybody have any thoughts?
I mean, all you're returning is one thing.
And are we even
So-
saving that in memory? Or are we just returning that?
No, just returning it.
Yeah. So when we're not doing anything like that, that's our constant, right? It's constant. It doesn't matter the size of n, the same space complexity, right? So it'd be O of 1. So here, the time and space complexity of this time would be equal to O of n. However large n is. N represents the array because we don't know how large that is. So n represents the amount of values in my array. And space is O of 1 because we're not saving anything, we're not doing anything like that. So doesn't matter however large n is. It's gonna be around the same space because we're not doing anything, right? That doesn't change. Now, can anybody think of a reason why it might sometimes be better to have a slower algorithm if it's got a more optimal space complexity? Anybody think of something that maybe, it might be slower, but it uses less space? Not this example, just, an arbitrary example in the world. Anybody have any ideas? Think about our current world and all of the items that we're currently using and have a circuit board, which it used to just be computers, right? But now lots of stuff has circuit boards. Most things, I would argue, have a circuit board. Sorry, it might be my internet, but it kind of cut out a little bit. Do you mind repeating that, Dontrell? Can somebody clarify if it's my internet or if it's Dontrell's internet? I can't really.
No, he's breaking up for
I
me
think
too.
it's his internet. I can't
Okay.
hear him either.
Cool. Let's think about this. I've got give me just 1 second. I'll show you. There are cool little kits that you can buy on Amazon. I'm happy to send you a link if you need that you can build your own tools. And they're about $60. About $60. The one I got is $60. You can get it for cheaper, but there's things like a Raspberry Pi, an Arduino sort of set, but this is a circuit board, right? It's got all of the different pieces in there. And this is finite when it comes to memory, right? We don't have this global server like we do when we're dealing with the cloud stuff, right? Like saving data on AWS is virtually, it's as much as you want to pay, right? You can save as much. They have servers after servers. They're building next to nuclear sites, nuclear reactors just to get cheaper electricity, right? That's growing forever. But when we have an actual IoT, it's called Internet of Things, or even this right here in my hand is a smart light bulb. There is a circuit board in here, right? That connects to Wi-Fi that I can control from an app, and it takes in signals and it does something accordingly, right? It does different colors or has a timer or whatever.
Hey,
Now-
Will, that Raspberry Pi, I think I saw you can like hook it up to a mirror and make it a smart mirror, right?
You
Stuff like
can.
that.
Uh-huh.
You can write your
can-
own code into it.
Yep. Raspberry Pis are very cool. That one's called an Arduino, Arduino. But you can do a million things. You can create weather systems, you can home security, a guy created a cool thing and he created a chair. It was like a thing next to his chair, and he connected an Alexa to his to it, and he had an Arduino set and built it. And he just said, I'm not gonna say it because I have one, but blank, make me a scotch. And he set his cup down, and it, with the Arduino set, it went under, poured a scotch, and then came back up, and he had a scotch, just like neat right there. So you can do a lot of really cool things with the hardware stuff. A million different things. I had a buddy who makes games with it, or it's really cool. If you're looking for a hobby, I'm not gonna, as an adult, getting a hobby is weird, but it's pretty fun to get into and like build little stuff and do LEDs and stuff. All that to say, those have limited amounts of memory, right? And so it's really important, especially as small as you get, when you're getting to like, this is a bad example given the world politics, but this is just a thought in my mind, but like a rocket, right? Right now we have rockets that have computers and a whole bunch of stuff that guided, like, computer guided, AI guided missiles. That memory, those are so small we're trying to get our footprint so small that it doesn't have a ton of memory. And so we might be okay with sacrificing a little bit of time with an algorithm if it gives us more space on our chip, or if we're doing something and we're really dealing with, we have some memory constraints, we might want to do a slower algorithm if it gives us better space complexity. So lots of other things, right? This is an RFID tag that you can, maybe a lot of apartment buildings will do this for like when you're entering in and out of a apartment building, or like your fobs for an apartment building. All of those have little circuit boards and everything that have memory, right? You're storing some piece of information. And so that space is really, really important. Those are usually written in like C or C++, because they do like pointers and memory allocation. But that might be something, or that might be a reason why we would want to have an algorithm or do something that really protects the amount of space that we're using, even if it takes a longer time. Does that make sense?
It's for a specific, so it's for a specific capacity or feature.
Yeah, or feature, or just depends on what you're doing, right? If you're going in and you're trying to get a job at Lockheed Martin, right? They might ask you, or if you're trying to work at like Google or Amazon and you're trying to work on their like devices in the sense of like an Alexa or a Google Pod thing, they might ask you like, okay, there's limited amount of space here. How can we handle this, or how can we manipulate this in a better way? If you're working on, again, Lockheed Martin, if you're working on things that are going to IoT devices, space is going to be an important thing because you have very limited amounts of it. And the less space you take up, usually the cheaper the product, in the sense of you don't have to buy, bigger chips. You can make them smaller, and people like small things. It's like Derek Zoolander when he had that really, really tiny phone. Does that make sense though?
Yeah.
Cool.
God,
Go ahead. Oh yeah.
God.
Yeah. He's got the little bit, he's like holding it like this. Very funny. Any questions on time and space complexity? Again, this was just to get our toes warm, to get our feet wet. I guess dip our toes, not our toes warm. That's a weird statement. To dip our toes, to get our feet wet with time and space complexity. There's a lot more that you can go into, because there's a lot more different possible complexities, right? We just talked about constant, linear, and quadratic, but there's exponential, there's factorial, there's logarithmic. If you have multiple things you're doing, you can combine stuff. So we'll keep adding into this and keeping this conversation. If I were to just sit here for an hour and talk in depth about all of those, A, I don't think I have the time. And in the sense of, I think I would need longer. And B, I think it would go way over your heads. So I just thought we could maybe, it's something that's a slow digest and something with practice. So.
Is it something that's monetized?
What do you mean?
Just in the world, like do we sell it like, hey, I have a app that's very good on time, or I could make your app run faster
Yes.
on time, and that comes okay.
Yeah, so faster is better, right? Think about the last time you had to wait for even an app to open. If you had to wait more than 5 seconds, you're like, what the heck is going on, right? Because we just want speed. And so oftentimes it's faster. So A, it is, we want things faster. B, depends on what you're using, but let's say that you're in the cloud, right? And you have something, so AWS has something called a Lambda function that basically you can have a trigger that whenever you ingest some sort of data, you can say, I want it to run this function. I want it to do something to this. And based on how long that's running, how long it takes to do, you're getting charged, right? If you've got a more efficient way to do something, you pay less money in the cloud, right? Because it's quicker to do versus it, if you're double for loop, that's going to take a lot longer than, if you did something, right? That's just an example, but then you're charging less money. or getting charged less money, so you're making money in that regards. The reason I bring all this up is similar to what we did yesterday with HackerRank. What will typically happen is you will have an algorithm that you are going to talk about. You're going to finish it. And then at the end, if you get it working, right, they're going to ask you, hey, what is the time and space complexity of this algorithm? They will ask that. That is a very common, every interview I've ever been in asks me the time and space complexity of the algorithm. So it's something that you do need to know. And so something you need to practice. Again, what is a good way to use AI? It is this right here. This is the best thing you could do as you're learning this. I would encourage you, don't write an algorithm without practicing the time and space complexity. Try to figure it out yourself. Get an idea of, oh, it might be this. Then go into ChatGPT and say, can you give me the time and space complexity of this algorithm? And let it give you that. And then see if you're right. And it'll give an explanation of it's because of X, Y, Z, it's this. And you're like, oh, okay, cool. I was wrong. This is why. And then the second thing to say is there a way to make this more optimal? And if so, tell me what you did and why it's more optimal. And then you'll just start learning. That's the best way you can use AI these next 3.5 weeks. Because then you'll start learning, okay, I'm seeing patterns. I know this. Also, a lot of these are using hash maps or hash sets. That seems to be faster. Maybe I'll start incorporating that into me building these algorithms.
So if you were in an interview and someone asked you what was the time space complexity, would your answer be like O of n, O of 1, or would you give a number?
You don't. So what I was trying to show at the beginning here was that we don't give numbers because there's too many factors. Like we can't give like whenever I had the actual time, like the 1.867, we don't give that. The way that we do it in computer science and as developers is we give the time and space complexity, the O of 1, any of these. So we would say, hey, if this was, let's say that you guys got a really good person and this was all you had to do, right? It was, great question. Because I'm only iterating through this one time, what I can tell is, even at the best case scenario, it's O of 1 because it's just the first value, but we don't do that. We do worst case scenario. And so because of that, there's a chance that either it's not in my array or it's the very last value. So because of that, I know I have to go through the entire thing, meaning that I'm going to have a time complexity of O of n, right? That's how I would address that. But yeah, whenever somebody's asking about time and space complexity, they're asking you to give them one of these values here. And you can expand on this. There's like n plus m, but we'll build up to stuff like that. That's like if your function is dependent on another function, right? And so you have to sort of, okay, it's however long this is plus however long this other one is. That's what that is, but something along these lines, not an actual value of it's going to take X amount of seconds or milliseconds. No, you don't do that. We always talk about time and space in big O notation. That's what this is called, is big O notation. So that's how we talk about it. Jennifer put a YouTube in the chat. Let's see. Hopefully I'm not getting rickrolled. Oh yeah. CS50 is like a legendary course from Harvard that's free. Everybody, lots of people know CS50. It's really, really, really popular. So, and this guy rules. So if you are interested, this is in the chat. And you can learn more about algorithms. CS50 is also just a great course to go through. There's a whole bunch. It's from Harvard. It's their entry level, but it's great on like binary and understanding. The first one's like all about binary and computers. It's cool. So CS50, I'm a big advocate. Okay. I'm going to stop the recording there.